Let me share my screen now. Can you see my screen?
Yep.
You can see, right? Okay.
Yep. Perfect.
Great. Let me know when to start then. Okay.
Yep. I'll let you know.
So I'll try my best to look at the chat panels as many as possible.
All right, so I think we're just gonna start. It seems like we don't really have too many attendees for this talk. Maybe just because you know this is 4 p.m. People sort of forget about that. That's okay. Yeah, for those of you who are here, so this is our last event. So you know, thanks for being here, and thanks for contributing and participating in this event. Yeah, so I think you know, we have Thiha here again talking to us about the various framework of computer or quantum computing. And again, this lecture will be recorded, and you'll be able to access this on the website. But yeah, so I think without further ado, Thiha, you can take the stage.
Right. Okay. Right. Good afternoon, everyone. Today, yes, I think as part of the last talk of this talk series, I will be ending this with again various types of the quantum computing frameworks that I'm supposed to talk about, like in my first talk, and as well as some of the quantum computing hardware architectures that are available at the moment in the research communities worldwide. So without further ado, let me try to recap a little bit about what I said earlier on in the previous week, right? So I mentioned briefly about this. Why is it so difficult to make quantum computers, right? There are a number of practical reasons. One reason is means that at the moment, I mean, you know, we've been controlling these different types of quantum particles or devices, macroscopic natures, right? And these devices, they are prone to various types of experimental noises, and also control parameter fluctuations and etc. Okay, so then the idea is that if we um, want to scale up these systems to like thousands of millions of physical qubits, and it is really a very challenging physics and engineering problems at the moment. Okay, so there is okay, and without going into details, right? And then also motivate by saying that okay, most of the time people are only familiar with the say gate-based quantum computers, right? And then as I put forward earlier on, that we need breakthroughs in this kind of hardware architectures in order to scale up this kind of existing quantum computer hardware. So it is also good to know some of the number of others quantum computing frameworks that are already available in the literatures, and also who knows, right? One days, one of you in the audience will be inventing your own types of quantum computing frameworks, and that will also help us in the develop these exciting fields. Okay, so I think in my last note I mentioned briefly about what is measurement-based quantum quantum computations, and we need cluster states, and how we arrive to this kind of a universal quantum computing and so on and so forth, right? So they basically one can prove that measurement-based quantum computation is equivalent to gate-based quantum computation. So they are the same, okay? And this is different types of frameworks that we have at the moment, right? And beside the measurement-based quantum computations, we also have a what we call is holonomic quantum computations. Okay, but this is a little bit challenging in the technical wise, and then again, this is a general published talks, and so I'm not supposed to use like heavy mathematical equations and so on and so forth. So I will try my best to explain the fundamental idea behind this holonomic quantum computation. So basically, what it is similar to what we have is here is like a McDonald's drive-through, right? And so basically, you are staying inside a car and you wanted to order something from McDonald's, and so you're supposed to drive through this particular pathway that you have, right? So this is exactly the same in the holonomic quantum computation too. What you do is that you have this kind of experimental control parameters. What I draw here on the right-hand side, right? This is the source of some sort of like a experimental control parameter phase space, so to speak, and you have three different types of parameters that you can control, which is F1, F2, and F3, and they can be drawn as like a 3D three-dimensional space, and so what you want to do is that you want to build a quantum gate, right? For instance, right, I have drawn here like a ACE gate operations, right? What it does is that it doesn't do anything. You just simply initialize your wave function. So basically, like you initialize your quantum systems in a particular state, right? And then you let it evolve through this three-dimensional phase space, okay? And now this is what I have written down here, right? Which is theta. Normally, theta is just a number, and in the community we call this it's a phase, right? But mathematically speaking, this number can actually be promoted to a matrix. I think there's somebody. Okay, I think this you have to talk to the organizer. I don't know the answer, and so so what I'm saying is that this theta can be instead of a number, it can be a matrix. Okay, so what it does is now is that this matrix, right, after the time evolutions going around through this phase space, and it will become a matrix, and this matrix is like similar to ACE gate operations that we are familiar with in the case-based quantum computations, and so this gate will then add on the initial state, right? Then in that way you will achieve a quantum computation. Okay, so again, why did I mention about this McDonald's drive-through is that, okay, because in here, right, I can also drive through in a different trajectory and different pathway, a difference than the highlighted red color line here, right? And then it doesn't matter, right? The point here is that what matters is that you stop at the counter ordering stuff, and then you left after collecting your order of food. Okay, so in a way, as you can see from here, right, the holonomic quantum computation has a clear advantage in the sense that it doesn't matter how you evolve your state. What it matters is that eventually it come back to the initial and the final points. Then at the end of the day, you will achieve this desired quantum gate operations, right? So it is robust against parameter fluctuations. Okay, so this is very, very interesting because experimentally this is a desired things, and so I don't want to go into a lot of details, but again, drop me a line also if you are interested more about this, or you can ask me at the end of the talk as well. Okay, with that, let me move on to the another types of quantum computations, right? This is called adiabatic quantum computations, okay? And again, this is see, here what you have is you have two different kinds of Hamiltonian, and one Hamiltonian is that this Hamiltonian is the grounds of this Hamiltonian is very easy to prepare experimentally, right? And then you have another Hamiltonian which is hard to prepare experimentally, and the grounds of this Hamiltonian encode the solution of the problems that you wanted to solve, right? In this particular example, or paper that I highlighted here, what you're trying to solve is the protein folding problems, and so so they initialize also here on the right hand side, right? You see the energy spectrums of this. Let me see. Somebody asked something. Okay. So this is the energy spectrums of the entire Hamiltonian as you evolve through time. Okay, because this is time evolving Hamiltonians, and so what you're saying here is right. You can follow this my mouse cursor here, right? So initially you prepare your system in some sort of a Hamiltonian H0, right, which is easy to prepare, as I mentioned already. And then the solutions that you want to find somewhere here, okay? And so what you do is that you just drive this Hamiltonian, varying this parameter through time, and as is required as the name suggests, right, it's adiabatic. So you have to evolve your Hamiltonian extremely slowly as compared to the energy gap of this the ground first excited state. Sorry. Okay. Right. Okay. So and then why am I keep saying this roller coaster figure here is right? It is the following, because normally this type of adiabatic quantum computation, the problems line first that this type of evolution has to be extremely slow. So sometimes it can be so slow. Again, it depends on the problem that you have, and so as I mentioned already. But again, there are a lot of technical details involved. Okay, so the time scale that you have to evolve this, how much the system, quantum system is dictated by the energy gap of this. Energy gap means the difference between this line and the line that you see here, right? And the larger the energy you get, you can evolve your systems faster. If the energy gap is getting smaller and smaller, then you have to move slower and slower. So it's not sort of like an inversely proportional to this energy gap square of that. Okay, so normally, right, for a general problem, these algorithms suffer from the slow time evolutions. At the end of the day, right, because quantum system has a particular lifetime, right? Probably some you have already had that from the previous talk, and they have this certain lifespans, and if this time evolution is much longer than this quantum system lifespan, then you know at the end of the day, even though you are already in this region here, right, your quantum system is already dead, right? And so basically what I meant is that your important informations are not available anymore. So then by right, you're supposed to get the solutions, right? But then because of the slow time evolutions, you suffer these issues. And the important analogy is this roller coaster ride, because in these problems, what normally researchers trying to develop is kind of like a shortcut to the adiabaticity approach or fast adiabatic algorithms, and there are a number of ventures out there at the moment, right? So the idea here is that this is very similar to the roller coaster rise, right? As you can see from the, as you can see, like the manifold of this energy is like the roller coaster track, right? And then and then how come that people riding on the roller coaster, they don't fly away, right? Basically, this is the issue with this adiabatic evolutions, right? So you have to drive it so slow that they don't fly away, right? But here, in a roller coaster, even though the roller coaster is moving so fast, and yet people are not flying off, right? So basically, because we wear seat belts, right? So there are a number of ventures in this research communities trying to develop, types of seed belts for the quantum systems, and such a way that you can evolve your system extremely fast, and yet it will follow the ground state manifold, and hopefully arriving to the desired solutions that we want. Okay, but again, yeah, a lot of technical details, and I don't want to go into all those details at the moment. Let me move on to the last one, okay, which is the topological quantum computations. This is the extremely exciting ventures, and it is the research directions where a lot of the physics and mathematics meet. Okay, and at the moment, I think Microsoft is the only company heavily invest on this topological QC approach to realize the quantum computations. And at the moment, I don't think anyone has realized any experiments about into this topological quantum computations. Okay, here the difficulty lies in the fact that one has to control a quasi-particles called anyons. Okay, and again, for those of you who are not familiar with quasi-particle, it doesn't matter, right? So we had about this like protons and electrons and neutrons, and so we learned this from the high schools, right? And so there's a new types of a quasi-particle called anyons, and there's these anyons. Extremely short lifetimes, and then so in this topological quantum computation framework, one has to be able to control those individual anionic particles into a certain what they call is a Braden's schemes, right? What I meant by this is the following, right? Here in this figure here, how you have to read this figure is that this time is going from the bottom to the top, okay? And there's this kind of there's this one particle coming up, and again it's split into two, and now you can somehow control this quasi particles into whatever you wish, right? And then by twisting around, like like in this figure here, like pastors, or like for those of the ladies in the audience, right, like braiding your hair, long hairs, right? So like twisting around in a different way, and by doing that, it is so people has already shown and proved that that is equivalent to braiding of these annual particles, equivalent to performing the quantum gate operations. Okay? And eventually then one has to have to do is then make measurements of those annual particles, and then get quantum computation done. Okay, so the good thing about this is that it is robust against errors. So basically, it has a built-in fault tolerance schemes in it, and so that is also the reason why Microsoft is heavily invested on this, and then we are looking forward to have some of the good news in the maybe 10 years down the line, right? So, and if any one of you are interested in this topological quantum computations, okay, this is as I mentioned earlier on, right? This is a combination of physics and, in particular, condensed matter physics and break knot theories in the mathematics and differential geometries. And so, it is a really rich research literatures out there, and I think this is the extremely well written book by Yanis Sparkles, Introduction to Topological Quantum Composition. So if anyone is interested, I mean, I highly recommend this book. And so with all these frameworks that I have mentioned, right? So as I already mentioned, right, these are hardware independent. So these are different frameworks, quantum computation frameworks available, and then now I would like to move on to discuss about some of the most popular quantum computing hardware to realize those different types of quantum computing frameworks. Okay, so this is as let me try to recall. So in my previous talk, I mentioned about this like different ways to define your classical mix, right? Like classical 0, 1 can be defined to be a molecular droplets, or in this case is a coffee stain, right? Like the intensity of a coffee stain can be defined to be 0, 1 of your classical mix, right? And in the quantum regions, right, we do also have different values to define your qubits, right? Here, as you can see, we have a superconducting circuits, and we have linear optics. We also have nitrogen vacancy centers, and we have trap ions, right? And we also have quantum dots, etc., right? And to realize different, say, gate quantum computations or measurement-based quantum computations, etc. Right. So let me try to go in details about, but again, details yet not very technical. I will go through all these individuals hardwares one by one now. So let me try to highlight a little bit about these superconducting qubits. Okay, so basically, in these regions, people realize two-level systems by just manufacturing simply capacitor indenters, and as you can see in these figures, this is nothing but LC oscillators, and in physics we know that. If we have this LC oscillators and we have this quantum harmonic oscillators, right? And then quantum harmonic oscillator is the properties of energy level equally spaced in the energy in this energy excitation spectrums, and as you know, we would like to have two-level systems, and this is not a very good system to realize two-level systems. So what normally did people in the literature in the community is you insert a nonlinear indenters, which is what we call is the Josephson junctions. And as again, for those of you who are not familiar with what Josephson junction, it's nothing but two superconductors. Let me see. Okay. So valid as holonomic QC, Diabatic QC, Topological QC don't use qubit. No, they do. They do use QC. They do use qubits. So let me try. Let me answer this quickly. So it's good that so let me just be a holonomic Idiopathic Topological. Right. Okay. So here, for instance, in the holonomic QC, right, as I mentioned, this is a single, say, it's a little bit complicated. This sign that you see here is a wave functions, and the wave function normally has more than two-level systems. So in principle, and in general, holonomic quantum computation can be made with four-level systems, right? But and then want us to work in a higher level excited states, and that's why you also have this instead of a phase you have matrix, and this matrix acting on this four level systems, and then you define your qubit to be in the lowest two level system of this four level setup, and that's how you define a qubit, right? So that's why, as I say, that is why you can exactly get by doing this type of evolutions, you can exactly get bifurcate operations that you see in gate-based quantum computations, right? And again, and then what you want to do is that now you want to scale up, right? Because one qubit is not enough, right? So we would like to have two qubit gate operations, three qubit gate operations, right? Yes, you can realize those as well in holonomic quantum computations, right? But again, the mathematics involved will be more complicated, but we stay use qubits. Okay, and here as well in the Idiopathic QC, again, this is a little bit tricky to see. In particular, Idiopathic QC is that now you are defining your problem as finding the ground state of ground state energies, and then it's not so clear, straightforward. I have to admit, right? But what you can interpret is that you have in a gate-based quantum computation, right? You see like a number of a line, right? Like this kind of this kind of a gate. You will have a chunk of gates, and you will have also have like two cubic gates, and was whatever, so on and so forth, right? And going from left to right, right? And then your algorithm run in such a way that you wanted to perform a particular operations, right? So now this entire problem is now mapped into can be mapped into finding the energy, ground state energy of this adiabatic evolution. So again, I have to admit that it's not clear, but this is how you should interpret it, and so whatever number of qubits that you have should be also appear in this Idiopathic QC as well. And here in the finally in the topological QC, as I mentioned already, these anyons will represent a qubit. Right, so and a braiding of those where be equivalent to performing different types of quantum gates. And again, I try to not go into details about those because it involves a lot of mathematical expressions, and then there's no point to go through this at the moment, right? Okay, I hope that I answer your question, Walid. Okay, now let me move forward by right. Um, uh, Here. And so here we have now after insetting, so and then this is here on the right hand side you have this SEM image of this single chosen junctions, and you see there's like a superconducting islands, and I don't think you can see a tiny layers of this insulating layer in between, but because this is like a sandwich on top of each other of the two superconducting material, so you can see it here, but there is a tiny layers of insulating materials inside, and so because of the device introduced in the circuit, your energy spectrum is now become enharmonic, right? And so then that means what I meant by enharmonic is that the energy separation between the 0 and 1 state is now different from the separation between 1 and 2 now, right? Because previously they are all equally spaced, right? And now here the separation between 1 and 2 is obviously different, right? And so again, if you go up to 2 and 3, it's even more difference, right? So it's clearly that you see that the lowest two energy levels of this superconducting system is defined two-level systems, and that is your qubit. That that normally people use in the experiments. Okay, and so I just want to highlight is that, okay, this is the type of superconducting qubits. And there are also a number of types of qubits. We call it a flux qubits, fluxonians, charge qubit, and X-mon, and zero pi qubits, and etc. Right. So here down here, right. So this is a paper that I took from 2015 from the John Martini's lab in the UCS Santa Barbara, right? Even before I think he moved to Google, right? And John Kelly was the postdoc in his group, and I think not postdoc. I think he's a PhD student at the moment in his group. And before the entire group moved to Google's, and these individuals plus nine that you see here is ASMONs, and ASMON is nothing but as a variance of transmons, and you have a control lines, and you have a control line here, and you have a measurements line here, and so that is how experimentally people try to manufacture this kind of chips, and doing the qubit manipulations and controls. Right, very good questions. So eventually, it's a good question. Normally, it is I have to give the another 1 hour thoughts on this transmon controls, and if you want me to explain this in detail, but I can say, and I can tell you roughly how people try to control this experimentally. Okay, so normally, again, in this figure here, right, this enharmonicity is not that big as well, right? So still like 1 and 2 is like almost equal to separation between 0 and 1, right? So if you drive micro again, the 0-1 separation is about gigahertz regions, right? So that is well in the limits of microwave. And so if you irradiate this transmon with microwave radiations exactly equal to this energy separations, right? And what happened is that, right, because the energy separation between 1 and 2 is also about the same as 0 and 1. In general, if you drive 0 and 1, you will also populate excitation to 2 as well, right? And this is really bad. And so one has to involve quantum control techniques. It's called, in the community, it's called Droskins. And I don't want to go into details, but what you have to do is that you have to find an optimal control pulse shape, right? In such a way, it's like a reverse engineering types of game. Like you wanted to have like almost 100% populations going into the one state, right? If you drive from 0 state, right? That is your goal, and that is your goal. Having this goal, what is the require pulse shape that you have to drive, right? And such that also you suppress that drive, you suppress the excitation going to 1 and 2. So this kind of thing has to be done, and that's a quick explanations, and I hope I answer your questions, Junji. And okay, so I think in the recent literatures, if I think a month ago or so, what people try to do is also using machine learning to control this kind of pulses, and see whether or not we can also find better gate pulses, structures, and stuff like that. Okay, so it is a huge huge community working on this kind of developing better controls and efficiencies, and then of course, you know, if you can control give a better gate pauses, then you improve the efficiencies and fidelities of your gate operations, and that is what we desire eventually, right? So there's a huge literature about this, and I don't want to go into that at the moment. Okay, now let me move forward in the remaining half an hour or so. It's a tri-ion qubit, right? And here, I think in the first slide, I mentioned about the metrics and metric movies, and I think in the last week talk as well, I mentioned about, like, you know how physicists are awesome, and we are able to stop bullets like particles, right? As you can see here, right? It's 1,000 meters per second, right? So basically, what you can see is a very nice cartoon pictures here. What it does is here is that again, this is a mechanism is called magneto-optical trapping mechanisms. Again, this is not exactly the same to arrive to the trap ions, but the ideas is about the same. Okay, and you have some sort of natural atoms. You heat up inside the vacuum chambers, and you pass through a Siemens law, right? Fuse and some profiles, and you have a laser that being coming in, and that's where they will slow down your slow down the particles, and then eventually there are 6 laser beams shining, and also you have a magnetic trap coming inside the vacuum chambers, and that's how you arrive to stopping the particles completely, like almost stationary, right? And ions is kind of like a similar mechanisms, but I don't want to go into details. But how people try to define a two-level system in the ion is a following, right? Like you can visualize in this picture is like, okay, you arrive to some sort of like ions, collective ions, or maybe individual ions in your trap, right? And then how do you define your two-level system? Naturally, right? So here I show you lithium ions that is typically used in the atomic clock experiments, and here I took it from my one of my unpublished work where we use this lithium ions to define qubits, and again, there are many terminologies. I don't want to go into details, but what I would like to highlight is that, right, natural atoms or ions, they have this energy spectrums that we have no control over, but is already defined by natures, and then we have to define some sort of hyperfine levels right here in this lithium ions. People normally use is that these two level MF equal to -1s, and S state here, right? This is a 0 state, and this is a 1 state for some experimental reasons that I don't want to tell. But there's also a shaving things that you don't really have to know, but that's how you experimentally defines 0, 1 state in a Trump ion systems, and then you have to shine a laser or light or microwave radiations to control and manipulate those individual qubits in the experiments. Okay. Okay. With that, I will end and move on to photonic qubit. Okay, in this year's very, very nice photonic chips architectures. I think there was published in Science in 2015 from the Jeremy O'Brien group in Bristol, where they show universal photonic chips control with a classical controlling and processing already built inside the chips, right? And these are the photonic chips, and so each line will correspond to like a photon, say micro photon propagation line, right? And then you have this kind of like waveguide architectures closing in between, right? That is the interaction regions where you can perform various types of gate operations, like, like single qubit gate rotations or phase gate or whatever it is, right? But what is fascinating is that what they show is that they can control those gate operations, and it's a programmable chips. So they can apply various types of classical pulses, and that will control those photonics waveguides, and then thereby again do universal quantum computations, right? But again, I think in my opinion, I still limited here is that, again, I think we are all from Toronto, and I think Xanadu is working on this kind of architectures, right? But I think they are working not in the micro, not in the single photon regions, but in there's a terminology of Gaussians, Gaussians, say they have these Gaussians opticals wave functions, and that is the qubits. Okay, but again, I don't want to go into details about that, but I just want to show you a different figure here, right? Here in this experiment is like photons defines like the horizontal and vertical polarizations to be your 0 and 1 qubit, right? But here you can, very interestingly, this is called optical orbital angular momentums light. And here you can have higher dimensional qubits, or what we call is a qubit, right? You can have d-dimensional bit, right? And that's how they define based on different helicity of your photons, and this is extremely exciting. Again. And then one can also use those as a defining information bit, and one can do a number of gate operations as well. Okay. Uh, with the remaining times, I would like to also mention about nitrogen vacancy center qubits. Okay, what is that? Is that you take your favorite diamond rings, right? And then as you know, diamonds is basically is a carbon crystal, and then these black white balls are carbons, and this is bonds, right? You have these valence bonds, right? Carbons in this in the diamonds, they have 4 valence electrons. And then here you have nitrogens. So experimentally, what you do is that you knock out one of the randomly knock out one of those carbon atoms, right? And then you insert nitrogen's atom into this vacancy, right? And then you also hope that there is beside these nitrogens, you hope that there is also another vacancy, which is an occupied place, right? Excuse me. And as you can see in this figure here, right, there's this nitrogens, there's a 2 valence electron bond, and in this vacant side, you have you have like one extra electrons, right? And so that is in community is called NV0 state. Okay, and again, this process is extremely random, and it's not so efficient to make this kind of nitrogen vacancy center qubit. Okay, it's a very challenging process as well. And what you do is that you attach this diamond to a external gate voltage, and then there will be another electrons coming into this vacant side, and it form a triplet state. Okay, and that triplet will define your qubits. So here, what I show here is 2 of the triplet state. right? MS equal to 0 and MS equal to plus state, plus 1 state, and that form two-level system of your nitrogen's vacancy center qubit. And then normally in this kind of experiments, you have to, because the energy gap between this MS equal to 0 and MS equal to plus 1s are in a microwave region, so you have to shine a microwave to control and manipulate this kind of NV center qubit. Okay. And lastly, we have quantum dot. It's basically the semiconductor qubits. In general, people use gallium arsenides and silicons to make these quantum dots. And basically, you have to manufacture as wafers, and as you can see in the cartoon here, right? And then you apply, and there are numbers of external gate voltages. And as you can see in this figure, there are two quantum dots, or supposedly there is a quantum well, and inside this quantum well there are two electrons sitting inside an electron spins, and they form a qubit, and again. And you apply different external gate voltages. Here again, in this quantum dots, you also have different types of operation regions. They are called a charge qubit, and there's also a spin qubit, and then so I don't want to go into those details, but I would like to highlight you a particular one, which is a charge qubit. Basically, okay, what it does is that you just apply external gate voltages, right? As you can see here, like you have a source and a drain here, and you have this as you can imagine, right? You have this like a batteries, right? You have electrodes on the left and on the right, so we call this a voltage left and a voltage right? And then by applying different voltages, you can have a different occupation number. Yes, a 0 is like or no basically say no qubits occupies, right? And then you have a 0 1 state, so there's a one qubit occupies in this in the right quantum dot, and 1 0 will be like there's a spin, there's a quantum dot spins in the left of the quantum dot, and so on and so forth, right? And then you have a 1 1 will be like you both of them will be occupied, and so on and so forth. So if you plot the energy spectrums, right, of these entire systems, and the energy spectrum is as follow, and that is where you see two-level system here, right? And I mean, in general, across these epsilon parameter regions, you have numbers of two-level systems, and I think in the experiments, probably where we are interested in this area around here. Okay. With that, let me summarize a little by saying that I have outlines different types of quantum computing frameworks, right? And then also and try to explain intuitively, and also in hand waving manners, without going into details about all the available quantum computing hardware, right? And then at the moment, right, we seems to lacking the experimental evidence of showing like a quantum computer performance outperforms classical computers in terms of performing useful calculations, right? Like because simply because we don't have a lot of numbers of qubits at the moment, and in my opinions, the way to go about is to combine different types, or either you invent a new types of quantum computing framework, or combine existing different types of quantum computing frameworks, and then building the hybrid structures of gate based and combined with adiabatic or holonomic approach, right? And so because holonomic quantum computations approach is robust against parameter fluctuations, and so if you try to invoke into the gate-based architectures, right? So you will be able to improve the efficiencies and performances, right? And then also, and there is a very, very interesting research ventures that I'm also very interested at the moment is that, as I mentioned briefly about topological quantum computations, right? And at the moment, well, what we see here in the literature is that one can take those very nice topological properties of the topological QCs and building into the superconducting circuit architectures, and then now again, this is still at the moment is a very early stage, and then now your two-level systems in your superconducting circuits are now quite robust against errors, actually, and then again, of course, those kind of hybrids chips are now again also very difficult to control, simply because that they once you open up the control channel, then the moment you open up, then the qubit properties will eventually disappears, and so there are numbers of there are a lot of problems to solve at the moment, right? So again, as I mentioned, so we need breakthrough understandings and discoveries in this kind of quantum hardware, both in terms of both theories and experiments, and of course that's reasons why we need so many young undergraduate students like Jews, right, to study physics and then discovers those major breakthroughs in the futures. Okay, with that, I will acknowledge my amazing meta labs in the U of T, and with that, yeah, I will take any questions from the audience. And again, if you have any other questions or if you're trying to ask questions, you may feel free to draw me emails or whatever you like. And I mean, I can also forward you some of the references to go into deeper uh, uh, um, in those areas of your interest, whatever you wish. Multi-state levels of accuracy. Oh, okay, okay. I think what? Okay, it's a good question. So, right. So I believe you are asking here, right? So yeah. So I'm just simply mentioning about this because it's really cool, right? In terms of pictures, right? Uh, and of course, there are. I would say there is no clearly why not we use. So the question is like, you should put in your questions into a different question, in the sense that, why are we interested in the qubits and not in the qubits, right? I believe that, I mean, if we can use qubit straight away and perform quantum computations, right? I think also that is also possible in general, right? I mean, there are a number of ways to explore, and that is one possibility, right? And again, this type of QAM lies are now used for a fundamental research purpose, not so much in the quantum computations, mostly in the quantum informations, because people are interested in, like, for instance, higher dimensional and maximally entangled states, and then uh, uh, I mean, I think in my last talk I mentioned about like 4 different pair states, right? And So one can also construct this kind of bare state structures, entanglement state in the high dimensional qubits, and people are simply interested for fundamental foundation reasons, and of course, if we can realize those, it is also is a very interesting venture as well. So that's why I just highlighted to you. Most of the time, again, I mean, performing gate operations will be extremely challenging for this QAM night as well. So I don't. Um, I have not seen, to my knowledge, I have not seen any literatures on this at the moment. Yeah, but in general, that is possible. Is there any questions? Any questions or any comments? I think now we are in a Q&A session, I guess. So, or if you like, you can switch on your mic and ask question as well.
Yeah, if you want to be unmuted, just raise your hand and I'll allow you to talk. All right.
Yes. So I just want to say, I think there is. I'm not so certain at the moment, but in the coming semester, I also just mentioned to Jamban as well. In the upcoming semester, our group is offering a course in the title is like quantum simulations, chemistries or so. So that is going to be offer coming semester, I believe, and I'm one of the lecturers there, and so I think we already have exciting number of exciting lectures prepared, and then it's going to be hands-on course. So you want us to do numbers of Python assignments, writing different types of simulations code to simulate gate-based. I think normally is in a gate, all those in a gate-based approach, and then. Try to realize different types of quantum algorithms and try to see getting. I think you guys has gone through this. Thompson taught yesterday, and I believe he mentioned about those VQE and variation algorithms, and then I think one of those lectures will be coverings onto those as well. And you can check it out. Yeah. Yes, topological QC is universal. It's no doubt. Yeah, it is universal because I mean, is a well, as I mentioned in my previous talk, right? I mean, in order to show universal, what you have to show is that arbitrary single qubit gate operations plus CNOR gate, right? And that way, that way surface universality, and topological QC has that as well.
All right. Is there any more questions from the audience? Any comments? And also just regarding what just regarding on what Thiha said about the course, we'll definitely send an email to you guys if you guys are signed up in our mailing list about that course. Okay. Seems like there's no more questions, so that concludes the our entire talk series. So thank you so much to Thiha, who organized this amazing slides and talks, and definitely appreciate everybody who showed up to participate. So thank you so much, and I think we'll end early today. Yeah, so yeah, thanks Siha for sure. But yeah, so have a wonderful evening. Christmas around the corner, so early Merry Christmas. But yeah,